Welcome to Geology 108. Today we're going to discuss the origin of the solar system and Earth. To understand Earth, we must place our planet in the context of the solar system, which consists of the myriad objects that are gravitationally bound to the Sun. Astronomers who study these objects have discovered several clues about the origin of the solar system itself. The solar system formed from a giant swirling cloud of dust and gas more than 4.5 billion years ago. The nebular hypothesis traces the history of the solar system through several evolutionary stages that ultimately led to the formation of the Sun, Earth, and other planets. In terms of our surrounding real estate at the largest scale, we are one small part of what is known as the local supercluster or the Virgo cluster of galaxies. A galaxy is an immense collection of tens to hundreds of billions of stars. Galaxies can appear as fuzzy elliptical shapes, can have big spiral arms, which is probably the most familiar kind, or can adopt a more chaotic shape. The key is that all of the stars are gravitationally bound to the galaxy. The vast region of space called the local supercluster is more than 100 million light years across, and it contains many thousands of galaxies. And our local supercluster is just one of thousands of known superclusters. Within the local supercluster, we are in the local group, which includes more than 50 galaxies, spanning a diameter of about 10 million light years. All of the local group galaxies are bound by gravity to a common center, which lies somewhere between our own big Milky Way spiral galaxy and our twin, the somewhat larger Andromeda galaxy, which is about 2 million light years distant. Our local group is just one of perhaps 100 groups in the local supercluster. Our galactic home is the Milky Way galaxy, which is a large spiral galaxy with between 100 and 400 billion stars. The age of the Milky Way, based on the ages of its oldest stars, is about 13.2 billion years, which is almost as old as the universe and suggests that stars and galaxies formed rather quickly after the Big Bang. Galaxies don't just form from stars. Galaxies are the engines of new star formation. As one generation of stars explodes or sheds its outer layers, it seeds space with the dust and gas that will become the next generation of stars. Scattered debris of old exploded stars are constantly subjected to the organizing force of gravity. Thus, remnants of former stellar generations inexorably seed new population of stars by forming new nebulas, each a vast interstellar cloud of gas and dust that represents the wreckage of many prior stars. Each new nebula is more iron-rich than the last, and each is a little poorer in hydrogen than the previous population. For billions of years, this cycle has continued as old stars produced new stars and slowly altered the composition of the cosmos. Countless billions of stars emerged in countless billions of galaxies. Nebulas abounded in our neighborhood of the Milky Way galaxy, and became the breeding grounds for still more stars. The Great Nebula in Orion, an immense nearby starburst region, is probably the most famous of all astronomical nebulas. In this image, glowing gas surrounds hot young stars at the edge of an immense interstellar molecular cloud only 1,500 light years away. The Orion Nebula spans about 40 light years and is located in the same spiral arm of our galaxy as the Sun. It can be found by the naked eye near the belt of 3 stars in the popular constellation Orion. Any story of the origins of our solar system has to take into account the distinctive distribution of planets, Plutoids, asteroids, and so forth. The formation of the solar system is described by the nebular hypothesis. The nebular hypothesis was first outlined by the French mathematician and physicist Pierre-Simon Laplace, who described his theory in the best-selling book titled The System of the World, which was first published in French in 1796 with the title Exposition du système du monde. The key characteristics of the solar system that informs the nebular hypothesis are as follows. First, the distribution of mass. 99.9% of the mass of the solar system is concentrated in the sun, with only about 0.1% in everything else, the planets, the moons, asteroids, comets, and so forth. The distribution of elements. Well, the inner solar system is dominated by rocky planets. These are Mercury, Venus, Earth, and Mars, with silicate minerals. While the other planets, the outer solar system, which is populated by Jupiter, Saturn, Uranus, Neptune, is dominated by hydrogen, helium, and other volatile elements and compounds. The theory of the origin of the solar system has to account for the distribution of angular momentum. The angular momentum is a quantity that depends on the mass of an object, its velocity, and its distance from a center of rotation. Angular momentum is important because it is a conserved quantity. The angular momentum of a system is always the same. And virtually all of the solar system angular momentum is in the orbiting planets, mostly in Jupiter because of its size. The orientation of planetary orbits and rotations is also quite unique. All orbits are in the same plane called the ecliptic, with the same orbiting direction. The sun and most planets rotate on their axis close to the same plane and in the same direction. I expect you to know the names of the planets of our solar system. Starting nearest the sun and working outward, they are the following: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and then possibly Pluto, which is far away from the others and does not have a stable orbit. Mercury, Venus, Earth, and Mars are terrestrial planets or rocky planets with a solid crust and mantle. In contrast, Jupiter, Saturn, Uranus, and Neptune are called the Jovian planets from the Jove, which is a Roman god for Jupiter. The Jovian planets are much bigger and made of volatile material. According to Laplace's nebular hypothesis, the solar system begins as a nebula, a giant cloud of dust and gas as a consequence of the competing phenomena of gravity, which pulls mass inward, and angular momentum, which keeps matter in orbit around the center of mass. In the case of our nebula, the cloud was likely gigantic, perhaps a light year across. The composition of our nebula was unremarkable, roughly 90% hydrogen, with various other elements. Later generations of stars have more of the heavier elements. Our solar system may have been preceded by half a dozen or more cycles of exploding stars. Gravity gradually attracted the nebular dust and gas into an even denser, more compact cloud, and the compaction of the nebula may have been assisted by a shock wave from a nearby exploding supernova. This process of compaction, once started, accelerated as the mass became more concentrated and the centralized force of gravity increased. Ever so slowly, the immense swirling mass of pre-solar gas and dust was drawn inward. Like a twirling ice skater, the big cloud rotated faster and faster as gravity pulled its wispy arms into the center. As it collapsed and spun faster, the cloud became denser and flattened into a disk with a growing and glowing central bulge, the proto-sun, which was to become the sun. As the proto-sun became larger and larger, gathering more hydrogen, its gravitational pull increased, so it became even more efficient at gobbling up the mass of the nebula. Ultimately, the sun swallowed 99.9% of the giant cloud's mass. But most of the angular momentum remained in the outer reaches of the nebula. As the sun grew, internal pressures and temperatures rose to the fusion point, triggering hydrogen fusion to make new helium nuclei, igniting the sun as a main sequence star. Every star is a balancing act between two competing forces. Gravity pulls inward, which causes the temperature and pressure to rise higher and higher. And then fusion reactions begin, adding more temperature and pressure and pushing outward. The ignition of the sun marked the beginning of the solar system, an event now dated at approximately 4.5 billion years ago. The sun defines the solar system, which is simply the region of space containing everything that is gravitationally bound to the sun: the planets, moons, asteroids, comets, dust, gas, and any other debris. The enveloping disk of gas and dust formed grains that collided and clumped together into small chunks or planetesimals. The terrestrial planets built up by multiple collisions and accretion of planetesimals by gravitational attraction. Giant outer planets grew by gas accretion, and planetary accretion increased throughout further collisions at the rate of centimeter per year over the course of the next few million years. Meanwhile, just after the protosun ignited nuclear fusion, it took some tens of thousands of years for that nuclear energy to work its way outward to the sun's surface. But when it did, a strong solar wind began to push outward from the sun throughout the rest of the solar system. The heat and wind from the sun stripped the inner planets of most of their hydrogen, helium, and other volatiles. That process left behind the 4 rocky terrestrial planets: Mercury, Venus, Earth, and Mars. Much farther out, it was cool enough for hydrogen and helium to condense into the 4 Jovian planets: Jupiter, Saturn, Uranus, and Neptune. The shared orbital direction and plane, as well as the similarity of the axial rotations of the Sun and most planets, is a relic of the original swirling nebula. Angular momentum is conserved, so the net rotation of the nebula is preserved to this day as the orbits and rotations of the planets. The nebular hypothesis of Laplace was embraced because it is simple, elegant, and it explains the major features that we observe today in our solar system. Nowadays, we can use computer models that keep track of the evolution of a dust cloud under gravity. Surprisingly, under most conditions, you don't get one star. In most computer simulations, 2 stars end up forming a binary star system. In fact, our solar system almost turned into a binary star system, which is otherwise very common in the universe. Jupiter is the largest planet of the solar system, with a similar composition to that of the Sun, which is 74% hydrogen, 24% helium, and 2% of heavy elements. And it is also similar to the composition of the solar system. Jupiter has a radius 10 times larger than Earth is, but 10 times smaller than the Sun. If more hydrogen from the nebula had accumulated in Jupiter, it would have ignited nuclear fusion and turned it into a second star. Instead, Jupiter has turned into the largest and most dynamic planet of the solar system. For example, the great red spot that you see in this picture is a persistent high pressure region of the atmosphere of Jupiter, producing an anticyclonic storm that is about 3 times the diameter of Earth and the largest in the solar system. All 4 terrestrial planets developed a common internal structure consisting of concentric spherical shells of different composition: a metallic core, a silica-rich mantle, and superficial crust. The Earth is unique in that it has a solid inner core surrounded by a liquid outer core. As a consequence of the stratification of terrestrial planets, the elements found near the surface are not representative of the whole. In fact, the most abundant elements of the Earth's crust are hydrogen, oxygen, sodium, magnesium, aluminum, silicon, potassium, and calcium, all lighter elements of the periodic table. The Earth's core is made of iron and nickel, 2 much heavier elements. Both iron and nickel are metals, which are very good electrical conductors. This allows the liquid outer core to generate a magnetic field as a byproduct of convection. The terrestrial planets of the solar system have a common structure due to planetary differentiation, a process of separating out different constituents of a planetary body as a consequence of their density or chemical affinity. Terrestrial planets developed into compositionally distinct layers. The denser materials sunk to the center, while less dense materials rose to the surface, generally in a magma ocean. As the dense material migrates to greater depth, its gravitational potential, a type of potential energy, is converted to accretionary heat, high temperatures. As a consequence, terrestrial planets have a warm interior and heat is exchanged with the surface through conduction and convection. For example, the temperature at the top of Earth's core is 3000 Kelvin. The temperature at the top of Earth's inner core is 5000 Kelvin, about the temperature of the surface of the sun. Earth is the only planet of the solar system with water in 3 different states: solid, liquid, and gas. The presence of liquid water for prolonged periods at geological timescales is thought to be key for creating and sustaining life. For this to happen, a planet should be not too close to its star, not too close that water evaporates and is eroded away from with solar wind. It should not be too far that the temperatures don't allow liquid water. We call this region the habitable zone or the Goldilocks zone. If this condition is found on Earth, well, how likely is it to be found elsewhere in the cosmos? We can address this question by exploring extrasolar planets. Powerful telescopes, both on land and in orbit, are providing amazing opportunities to detect the presence of planets orbiting relatively nearby stars in the Milky Way. It is not yet possible to see most exoplanets directly in a telescope, but various techniques have been developed to reveal their presence. The technique that was used first to identify hundreds of planets beyond our sun involves looking for a slight periodic wobble that is caused when a star and one of its larger planets orbit around a common center. As many as half of all sun-like stars may have planets. And our Milky Way galaxy alone may hold more than 100 billion planets. A significant portion of these planets may be in the habitable zones, like Earth, with liquid water, the elements of life, and a wealth of different rocks and minerals. These findings show that the conditions to generate life are in fact ubiquitous in the universe. So the odds that life exists out there, and even perhaps intelligent life, are finite and even very likely.